All right, we're talking about section 1.1, linear equations, and I'm to the example where we have fractions, and I wanted to talk to you about how you can clear the fractions to any equation before you get started with the other steps. So what you want to do is you want to look at every term. In this problem, I have a 3, a 2, a 4, and a 3. All of those will divide evenly into the number 12. Even if you use 24 or some larger number, 48, it would help reduce it. But the least common denominator would be 12, so it'll keep the number smaller. But you can go with a larger common multiple, and this will also work. But anyway, 12, we'll notice when we distribute it to the left side, we have to also times it to the right side to keep the balance. What basically happens is it multiplies through by every term. Each one of these terms, 1, 2, 3, 4. There's 4 terms in this problem. All of those get this 12 applied to it. So multiplication is distributive, so that's why it's just basically running through every term, and this will help us clear the fractions. When we multiply by 12, diagonals can cancel. 3 divides into 12 4 times, and then the 4 is what's multiplied to that numerator. And then there's no denominator, so there's no fraction. So 4 times that, that's where I'm at. Then you have to take the 12 again, so I know you probably aren't working on a marker board, but for me, I'll just erase it. I'm going to use the 12 again. 12 distributes here, 12 times a half. Again, that canceling diagonally makes that just a 6 times 1, 6, and then it has an X on it. For this side, again, and you can use your calculator on these and check it out, 12 times a fourth would be 3. And that happens because 4 divides into 12 3 times 1, 3x. And then lastly, 3 into 12 is 4, then 4 times 7, 28. No fractions then. Nice, clean equation without any fractions to bug us. Then we proceed with our steps, distributive. Combine any like terms on each side. 14 x's on this left side and 16. Take your variables to one side, so minus 3x makes 11x. 16 to the other side, minus 16. Negative 28 plus negative 16. You're combining these, so you're adding basically. Would be negative 44. Bring down your equal sign. Last step is divide by the 11, or 1x, or x equals negative 4 for that one. And then we should be able to check that back in and verify it works. So the next one, I'd like for you to pause the video, try that one on your own before I reveal the answer so you get your active learning practice for this. So number 4, the problem looks like this. Fractions all over again. Same strategy we want to use here. Times through by the LCD. So the least common denominator, or the least common multiple that all of these denominators fit into, is 10. So we're timesing each side by 10 to clear the fractions. It's just this beautiful algebraic method that will help us be able to solve it without the fractions to distract us. When you distribute the 10, it basically multiplies onto every term. Because the 10 is really 10 over 1, it's diagonal, so you're dividing the diagonals, and it just cancels it out on that one. It brings down the 3x plus 6. You have to use the 10 again for each term, 10 or 10 over 1. And you might just kind of innately know 10 times a half is 5, but this process works here too. 2 into 10 is 5. 5 times 1, that's the 5. Bring down the x. Here, again, you can use your calculator. If there's no x on it, like this 2/5 times 10, you can verify that should be 4, but it's because 5 into 10 is 2, then 2 times 2 is 4. And don't forget your variable to bring down. And then this one will be 66. Simplify each side. 3x minus 5x is negative 2x. Then we want to bring our variables all to one side and our constants to the other. So minus 2x to the right side becomes plus 2x for a total of 6 x's. 66 to the opposite side is minus 66. Thinking ahead of myself there. 6 and minus 66 is negative 60. Last step, divide by what's with your variable, dividing by the 6 for an answer of negative 10. Just remind you, when you're dividing, when the signs are different, it is negative. So that's the negative 10 there. And then again, that should check out. Okay, you have another one of those. Again, I wanted to really emphasize clearing the fractions on these. That's kind of an important strategy. It comes up every once in a while. Wanted to make a big point of that while we're solving these. So one more time. Fractions all through this one too. A lot of times there's not fractions on every term, but even if there's a fraction on just one term, you want to clear it. You still have to times by whatever you're doing. You have to distribute to every term, but it will help just to get rid of, even if it's just one fraction. I advise this strategy. So 4, 5, 2, and 5. The least common denominator for that would be 20. We're going to need 20 for all of those to fit into it. So 20 times every term, 20 times 7 fourths, we divide, which is 5, and then multiply what's left, 35. So it's divide, then multiply. Go back to the 20 each time. 5 divided into 20 is 4. 4 times 1, 4x. 20 times 3 halves, 22 into 20 is 10. 10 times 3, 30. Notice no fractions, that's great. On this side, you also have to apply the LCD to keep the balance. So times in each side by the same thing is critical to the concept here. So 20 over 1, you divide diagonally 4. 4 times 4 is 16, and don't forget your x. Okay, so that's the strategy to clear your fractions. Combine any like terms. 35 and minus 30 is 5. So simplify each side as much as possible. Then variables on one side, constants on the other. So there's only one constant, so I'm going to let it set still and take the 4x to the other side, making it minus 4x. 16x minus 4x is 12x. And then there's the 5 on that side, just 5. Then the last step is always divide by what's with your variable. So the 12 divided by 12 to make a 1x, or solving for x. What you do to one side, you do to the other side for a fraction answer of 5/12, like that. Okay, so that's the fraction stuff. Next, I want to do an example with decimals. It's a similar strategy, but a lot of times students don't mind the decimals as much as fractions. We're used to working, I think, in decimal world due to our money system, dollars and cents here it looks like. So if you want to keep the decimals in it, and sometimes it is probably just as good, easy to leave the decimals in it as not, but just know this strategy also works for decimals. When you look through this equation, there's 2 decimals to overcome, really the hundredths place. So if I would multiply by 100, times it by 100, 2 zeros, moves this 2 places. Now, even though this one only needs 1 place, I got to go with the largest one, kind of that least common multiple thing. And it'll take care of the other ones as well. If there would be one with 3 decimals, then I'd have to times by 1,000. So whatever amount of zeros to overcome all the decimals. So anyway, 100 will do it. So I take 100 times both sides. Multiplying by 100, again, we're distributing. Multiplying by 100 moves your decimal 2 places. It makes that just a 1x. Now, even though this one only has 1 decimal, because I'm times by 100, I have to go 2 places, making that 310. And then 2 places here, and 2 places here. And then this is a completely equivalent equation. It's the same equation, just a different form of it. So it's okay, you know, in general, in math, it's a big concept that we follow all the way through the course. It's what you do to one side of an equal sign, you do the same thing to the other side. It keeps it balanced, and whatever kind of cleans it up or makes it a better form for you. So now I want to bring my x's to one side, so I'm going to bring this 1x over, making it minus, leaving 2 x's. Then the constants to the other side, so plus 296. Bring down your equal sign between it. Divide by what's on your variable, whichever side that may be, to make your 1x or just x. And this one should be x is 3. Whether you worked it with the decimals or you use the strategy of cleaning out the decimals. Either way, same result. All right, and again, all of these have been conditional equations, just to remind you of that wording that you're going to need when you do your homework. A conditional equation means you got the answer. It works with the condition that x equals that number that you found. But we're going to see on this number 7 and 8, the special cases come up here. Notice on number 7, and again, please do pause the video and work these before me to get yourself active learning and practice on these. But I'm going right ahead and just counting on you to do your own pausing as you need to on these. If we were in class, I would definitely pause and we'd work them together. So kind of emulate that at home. When I combine the left side, I have negative 2x and 3x, which is 1x and a minus 8. Well, look at the other side. It's exactly the same. You've got an x minus 8 on the left and an x minus 8 on the right. Completely equivalent, mirror images of each other. When that happens, that's called an identity. That's the type of equation. And really, anything you plug in for x has to work. If x is 2, 2 minus 8 equals 2 minus 8. If x is 3, 3 minus 8 is 3 minus 8. If x is any real number, it's going to work. Now, what it looks like algebraically, if you keep rolling with it, is the x's drop out. You lose your variable, and you have what's left is a true statement. Negative 8 equals negative 8. So identities look like true statements or mirror images of each other, and the solution is all real numbers. Any number that we plug in for x has to work in that equation. On the other hand, number 8 is going to be our false situation, our last scenario for what can happen when you're solving through these steps. So again, practice working these ahead of me. You get 9x minus 3 equals 9x plus 7. So you might just think about it and just innately know, like, that can't work. You can't times something by 9 minus 3 and get the same thing as that same thing times by 9 with a plus 7. So it doesn't make sense. It's a bad equation. There's no solution to that. But if you keep going through the steps, what happens when you bring your 9x over? 9x and minus 9x, you know, the x's drop out, you lose your variable, but this time you're left with a false statement. So when it's a false statement, that means there's no solution for that. There's no way you can get that to work, and the type of equation is called a contradiction. It's just a contradiction. You cannot solve that and get it to work. All right, the last part of your lesson, we're going to talk about solving for specified variables. I'm going to go ahead and pause the video here and come back in the next one and do that last little section. So I'll see you in a bit.